So what are you guys?
We're part of the SWARTWOOD family!
For this first lesson, I want to get into quantum numbers. I want to keep it pretty mellow and just give us what we need for the exam, okay? But I also want to use this as an opportunity to set up some framing for stuff we'll do later, okay? So the first thing is, you remember the old high school lie or junior high lie? Which is basically you've got the nucleus with neutrons and positive protons hanging out. So neutral neutrons, positive protons, some sort of positive nucleus. And then you have the electrons kind of running in orbits like this, very roughly. And the electrons are, of course, negative. Okay, so the thinking was roughly, the farther out you are, the more energy you have. And why is that the case? Because how come this piece of chalk has more energy here? At least it feels like it does, right? If I let him go, it's going to go and smack the ground than if he's just sitting on the ground. So if we look at it this way, if you, negative likes positive. So if you were to let this guy go, this sucker would literally crash into that positive. And if you were to let this guy go, he would crash into that positive, right? Theoretically, if we kept this super simple and just use classical thinking, this would work, right? This guy goes this far, this guy goes that far, this guy does something for you, this guy does more. If he can do more, he has more energy. So the farther out you are, generally, the more energy you have. Okay? So one of the things that encapsulates that idea is the principal quantum number. So that's number one. So the principal quantum number. Okay? And the principal quantum number n, what is known by n, right? That can range from the first to the second to the third to the fourth to the fifth out to infinity. Okay? This is what I like to think of as the old school version of energy level. The higher the energy level, the more energy you have, because roughly, the farther out you are. Okay? And if you're farther out and you come crashing into the nucleus, you can get more done. Okay, but now, let's leave behind the high school lie and go to, I guess, some better lie. So now you've got this nucleus again, but this time we know that the electron doesn't go in a perfect orbit. In fact, it doesn't even come close. It's doing something kind of like this. In fact, the world of quantum is so confusing now that basically nobody, living or dead, really understands it. Okay? And they can do the math, they can do all that, but no one really can wrap their head around intuitively what all this stuff means. So we're just going to keep it simple. Okay? We're going to do an approximation here. We're going to think of it like this. We don't really know what the electron's doing. It's like all over the place. Maybe it's not even moving. Maybe it's smeared out. Is it in one place? Is it in many places? Super confusing. But what we do know is you're more likely to find the electron here than you are, say, way over here. Does everybody agree? So at least we have that you're more likely to find an electron here than you are way over here. So we have some idea. It's not a perfect orbit. It's like this kind of wannabe orbit type thing. So I call it an orbital. Okay? Now, if you're really into chemistry, you know that this whole thing, the principal quantum number, all that will basically give us an orbital. Okay? But I want to keep it simple. I want to think of this as the distance from the nucleus. And what I want to think of number two as is roughly the shape of the region of space where you're likely to be found. Okay? So I'm going to think of that as the type of orbital. Okay? So the simplest is, of course, you can be found symmetrically around the nucleus, and that is the s orbital, right? Another one up is going to be the p, where you're kind of in this dumbbell shape around the nucleus. Okay? Of course, for the purposes of the MCAT, the only shapes you should really know hardcore are just the S and the P. Okay? I'll keep this going, though, just for completeness and show you some examples. The D, you can visualize them to have a rough approximation as having more dumbbells. So D would kind of look like this. Please don't get this confused. This is not two P's together. A p orbital, the electron's either here or here, somewhere like that, but not likely to be found here or there. But in a d orbital like this, you can be found here, 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 or here. Any of the four lobes is pretty much totally fine. Okay, so now let's look at this. So for an f orbital, sorry, it's supposed to be an f, you can think of that roughly as just more dumbbells. So now 3 dumbbells, like this. Okay? Now, it is true when you look in your textbooks and all that, there are other shapes that go along with these guys. Some of them look more like, you know, dumbbells with little hoops on them, et cetera, et cetera. I wouldn't worry about that for our exam. It's enough to know that the principal quantum number gives you roughly total energy and distance from the nucleus. The next guy, which we've done so far here, gives you a description of the type of orbital you're dealing with. Okay? Meaning roughly like what shape are you taking around the nucleus, whether that's S, P, D, or F. Okay? And so that guy's actually going to be called the angular momentum quantum number. Okay? Another name for this is the azimuthal quantum number. For reasons that we don't need to get into here, but if it really stresses out, you can message us and we'll talk about it. This angular momentum quantum number is tied in some sense to momentum, the way you think of it, like angular momentum. I always want to be careful when I say things like that because the quantum world doesn't really like the classical world that much, but it's all good. But now, let's say for S, it's easy, right? There's only one way you could be spherically symmetric around this guy. It's just a sphere. Okay. But What about, for example, the p orbital? Do you guys agree? If we're dealing with a p orbital, right? And you have your nucleus here, and one p orbital fits in like this, right? There's still enough room for you to actually squeeze in, if you felt like it, another one that does this. Does everybody agree? And it's hard to draw, but there's even enough room to have one coming out of the board and going into the board. I'm just going to draw it like that. Okay. So you actually have enough room to squeeze in 3 different p orbitals. So just knowing the angular momentum quantum number tells you you're dealing with a p orbital, but it doesn't tell you which one you're dealing with. Okay? So for our purposes, you can say this. If I were to name these guys, I'd name them like smiley, frowny, and confused. Okay? That's totally fine. But you know how chemistry geeks are. They don't like doing that. They want it to be a little bit more precise. So we should give them names, like mathematical names. Okay? For example, we can call one of them randomly -1, 0, and 1. Okay? It's not quite as arbitrary as this. In real life, when they're doing this, you're looking at Schrodinger's equation. You're getting these quantum numbers. The numbers come out like this. And now what we're doing is we're trying to interpret what those numbers mean. Okay? Also, it does, in some sense, represent the angular momentum you have around that z-axis, where we arbitrarily define one guy as being a z-axis. Okay? But for our purposes, it's just better to think of them as labels. You have these 3 different p orbitals that hang out in space, right? And if we can all agree upon a set convention, right? And I told you, oh, we're dealing with a smiley p orbital, you know exactly which one I'm talking about. So for us, effectively, that's what these numbers mean. These numbers will tell you exactly which orbital we're talking about. Okay? So over here, I'm actually going to move this over here, running out of board space. The third quantum number is going to be called the magnetic quantum number. Okay? And that tells us roughly the exact orbital we're talking about. Now I'm going to backtrack and give us numbers for both the angular momentum and the magnetic quantum numbers. Okay? But I kind of want to do them together, and you'll see why. So for the angular momentum quantum number, which is represented by L, this guy can take values from 0 to 1 to 2, all the way up to n minus 1, where we're tied to that principal quantum number. Okay? All right, so let's talk briefly about this. It's so not important for the MCAT, but sometimes I get a lot of questions in class about why doesn't this guy go all the way up? I mean, if it makes you feel better, the reason why L cannot be equal to M is this guy represents, in some sense, total energy. Okay? And this guy represents, in some sense, rotational energy. But the thing is that if you have a guy, an electron, say in a p orbital or something, and it's kind of rotating around the nucleus like that, if L were equal to N, that would kind of mean, in some sense, that all the energy you have is from circulating around the nucleus. But that can't be right, because some of the energy you have, as we argued before, right, is purely from distance from the nucleus. So you have to have some of your energy tied into distance from the nucleus, so it can't all be invested in your angular momentum. Okay? So that's roughly it. If that bothers you, don't worry about it. You can be like, I believe it, right? So the best way to think about this so far, as a quick recap, is total energy and distance from the nucleus, more or less. The type of orbital you're dealing with. And now we're going to talk about the exact orbital. Okay? But do you remember, well, before I do that, my bad, we should decipher these. So what about these L values? So L equal to 0 goes to our s orbital. L equal to 1 goes to our p orbital. Okay? L equal to 2 goes to our d orbital. And L equal to 3 goes to our f orbital. Okay? So now, let's go back. Remember for the p, we had 3 of them? And I just told you randomly it was -1, 0, and 1. Let's actually get those names. So the magnetic quantum number, m sub L, is given by -L up to 0 up to L. These values. Okay? So what does that mean? Well, let's say, for practice, L0 is S, L1 is P. So when L is equal to 1, you're dealing with a p-type orbital. But we already said the 3 p orbitals, right? Smiley, frowny, or confused, or -1, 0, and 1. But if we just follow this formula and we trust it, if L is 1, the values could be what? -1, 0, and 1. So as far as we're concerned, these are the specific names for the different p orbitals. And since you have 3 different names, you must have 3 different p orbitals available. Okay? You probably remember from school that for L equal to 2, when you talk about a d orbital, you know you have 5 d orbitals available. But let's actually figure that out. Because then the names here will be something like this. -2, duh. -1, 0, 1, and 2. And again, 1, 2, 3, 4, 5 names. 5 names implies there are 5 d orbitals, right? And for L equal to 3, let's just complete it. You have an f orbital. But again, if we just follow the formula, it's going to be -3, -2, -1, 0, 1, 2, and 3. I don't know if it really counts as a formula, but you get what I mean. Okay? But again, we have 1, 2, 3, 4, 5, 6, 7 names. Therefore, we must have 7 f orbitals available. Okay? All right, so are we good yet? We're trying to find that exact electron. We know roughly how much energy it has. How far are you from the nucleus? We also know what type of orbital it's occupying. We know now the exact name of that orbital. We've got it down to that. But the thing is that in any given orbital, you can have 2 electrons. So because of that fact, we still don't know exactly which electron we're talking about. So to get that exact electron, we need a 4th quantum number, right? And that guy's called spin. Okay. And again, the designation, as far as we're concerned, we could have called it smiling and frowning, but they have 2 designations, spin up and spin down. The truth is, again, they're running this equation, these numbers pop out, and now we're trying to interpret them. Okay? Okay, but spin up, represented like this in electron configuration, which we'll do later, and spin down. Okay, no big deal. So plus a half minus a half. Now if I give you all 4 quantum numbers, you can tell me exactly which electron we're talking about, because you'll know roughly how far out it is and its total energy, right? You'll also know the type of orbital you're dealing with. You'll know the exact orbital, actually, and now you'll have it down to the electron itself. Okay? So all 4 quantum numbers give us uniqueness. Okay. All right, so not too bad. Usually at this point, we talk a little bit about the Pauli story. So Pauli came in, and so you had these guys, and they're working on this, and they basically more or less discovered spin. And they went in and they told Pauli, who was a resident chief, chief of staff at the time, more or less, hey, what's going on? Like, we discovered something, maybe this is important. And supposedly the story is Pauli looked at them and went, you guys are idiots. If you release this and say this, you're going to be the laughingstock of the community, et cetera, whatever. Just start all over. So the story is they tucked their tails between their legs. They walked out and went, oh, we have to start all over. But when it came down to it, I mean, who's going to know how it really went down? Supposedly, Pauli just sat right down and decided, ooh, I'm going to write this up. And he wrote it up. And for a while, people thought this was all Pauli, when it really had nothing to do with him. Okay? But all good.